All right, welcome. So where was the Zoom passcode located? On the front page. Where are the slides located? And class notebook. There you go. And what's the third question? Oh yeah, what's the maximum grade possible if you do just the homework and the quizzes? I want to say not 80. Uh, with the extra credit, yeah. Well, that is if every single student submits every single evaluation every single week. Then we could go up to like 5. Yeah, so you could potentially end up with like an 80 or 79.99. But no, the question was maximum possible grade, so yeah, 80. All right, let's see. Uh, let's go to our class notebook. So it's synced just in time. So you have the slides in PDF form. You also have it in the OneNote in case you want to make notes along, alongside mine. And then okay. All right. Introduction to electronics. What is electronics? Well, just a little bit of background, right? You've all taken 113, 211, and 212, right? At Cal Poly, we're in the quarter system for one more year. Electrical EE students take 3/4 of circuit analysis, which translates to one entire academic year. If you're at a semester-based university, it's the exact same thing. You spend one entire academic year taking circuit analysis. It's called Circuits 1 and Circuits 2. When I was a student more than 35 years ago, I did the exact same sequence. So you took circuits, that was the most fundamental of classes. Now is the most fundamental of semiconductor classes. So semiconductors and semiconductor devices. That's what you're going to learn here. So right now, currently, I would say we don't have a clear demarcation or delineation between electric and electronics, but technically we would classify electric as linear elements comprising of resistors, capacitors, and inductors. And then nonlinear elements like diodes, BJTs, MOSFETs, FETs would be classified as electronic devices. Okay. With electric circuits, we learned about techniques. You learned about Ohm's law, KVL, KCL, node voltage analysis, mesh current analysis. I hope everyone remembers all of those, by the way. Thevenin and Norton, hopefully. So those analysis or those analysis techniques are referred to as analytical analysis techniques. Okay. The equations are exact. The solution is also exact. All right. And so that's what we mean by analytic analysis, and that they're predictable. Ohm's law, for instance, one of the simplest but the most fundamental of laws in physics and EE, V equals IR. Voltage is directly proportional to the current as pertains to a resistor, right? If voltage increases, current increases. If current increases, voltage increases, right? And the equation is V equals IR. You plug in, if you know any of those, if you know two of those quantities, you can calculate the third. So it's predictable. Nonlinear elements, not as much. Okay. We are concerned with transformation of energy in both cases. But in nonlinear elements like diodes, BJTs, and FETs, we use numerical methods. Our results are not always exact. More often than not, they are approximate. Okay. And to describe these devices, we use different models. For diodes, for instance, there are 3 or 4 different kinds of models that we will study. There are much more than those. Depending on your use case scenario, we can use a simpler model. If you want to save time, use the simplest of models, which is known as the ideal diode analysis model. There's offset diode model. There is also there's there's numerical methods. We use mathematical equations to determine the quantities for voltage and current. So difference between electric and electronic, not just in terms of the components that we are studying, but also the methods that we use are slightly different, right? Depending on our use case scenario, our models will be different, right? No single model will be able to describe a device in all use case scenarios. If the temperature is different, if the pressure is different, the environmental conditions are different, we need to use a different model. Oftentimes, if you have looked at data sheets for any electronic device, whether it's a microchip or any other kind of device, it'll always say this is rated between certain temperatures. And then you always hear about military spec, right? Mil spec, MILSPEC. Well, military spec devices are used in extreme environments, from the hottest places on Earth to some of the most coldest places on Earth. And so those devices are designed differently. They use different kinds of models. If the same diode that we use in the lab cannot be used in a military application, it just would not work. Okay, it would freeze up and not work. So different models are required. And that was one of the points or purposes of having that. Okay, describe yourself in 10 words or less. One is the larger purpose. It's a legitimate interview question. Somebody might ask you in an interview, describe yourself. And what is it that you can't just start to think on the spot? You should have something prepared beforehand. Okay. So depending on our requirement, we will describe each device with a different model. All right, so in E306, we're learning about some semiconductor fundamentals. We're going to develop different models for these devices. 307, you're going to take those techniques, going to apply it for digital logic circuits or digital circuits. And then 308 is about analog electronics, so analog circuits. And then you put it all together in 409, which is electronic design, which is mixed signal electronics. Okay, so this is just basically at Cal Poly. Just wanted to give you a little bit of an overview of where and how you're going to use these going forward. All right. Whether it's digital or whether it's analog, the circuits or the components are the same. It's simply a matter of looking at it, right? So a light switch is an example of a digital application or digital circuit. Light switch has two modes or two states, either on or off, 0 or 1. However, if you have a light dimmer that has infinite levels, not just a click, 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 let's say a smoothly rotating knob like a dial, and you're dimming the lights, now you have infinite possible levels. Depending on the physical rotation of the dial, the value of the voltage or current that's going through that light changes, and so the light intensity can be varied. Okay, that's analog. That's it. Same. So analog circuits and digital circuits, pretty much the same thing, but the analysis is a little bit different. Okay, evolution of electronic devices. And in the days of the vacuum tubes could be small, could be large. Anyone ever seen a CRT television or a television display? Cathode ray tubes, the big televisions from my time back in the day. That was a vacuum tube. There's an actual vacuum tube, right? Now, these vacuum tubes that you see in front of you, they are small. These are small devices, right? The earliest known vacuum tube had only 2 electrodes in it. Had a cathode, had an anode. And we'll talk about it when we get to the semiconductor diodes, right? So these vacuum tubes were designed or were devised or created as a means of controlling the flow of current between 2 terminals in a circuit. The simplest of vacuum tubes had 2 electrodes, one anode, one cathode. And when you applied a potential difference between the anode and cathode, you could actually control the flow of current, the flow of ions between the two, right? And so that's when they discovered that you could actually manipulate the flow using like multiple electrodes. So a diode means 2 electrodes. You insert a third one in there and you obtain a triode. Insert a fourth, you get a quadrode, pentode, hexode, so on and so forth. I think I've never seen a vacuum tube with more than 3 electrodes in there, but I've seen images on the web and the internet that had like more than 10, 15 electrodes. I never even studied those. I have no idea, but we did study vacuum tubes back in the day. All right, so from vacuum tubes, we then move to discrete transistors. We'll talk a little bit about the history of these transistors. So these are transistor devices. All of these, by the way, that you see in there are simply packaging. The actual semiconductor device is very small and very tiny. We can't even see it. Okay, so all of this that you see in there is simply packaging. All right, the reason for the different kinds of packages, first is standardization. And the second is, of course, depending on the power handling capability, we need large heat sinks attached on them. And so this is kind of like an example of a power transistor. You can attach it directly onto a heat sink for dissipating large amounts of heat. All right, from discrete transistors, we went and created the integrated circuit. Okay, and so first there was small scale integration. So it came to be known as SSI. And then came medium scale integration, MSI. And then finally, it went to large scale integration, LSI. And then currently is actually LSI. There's too many V's in there, but obviously you can see we just stuck with VLSI, which I think is a good choice. So very large scale integration, VLSI, that's what it stands for. It simply means you took a large amount of components and you put it onto one single piece of semiconductor material. That's all it means. Professor Nishit Chakrabarty, she joined us last year. She now teaches the advanced courses in VLSI. I think there's a 400 level and a 500 level class that she teaches in 126 right there, right across the hallway. And so once you are done with our 300 level classes and you go to 400 level, if you wish, you can take one of those classes where you learn about VLSI architecture design. And so, yeah, that's very large scale integration. Simply taking a large number of components and putting it in there. Modern electronics era. Oh, just a little tangent. VLSI, nowadays, when you hear about VLSI, they always talk about microchips and, this company is making a microchip and this company is making a microchip. Well, there are two parts to this. And this is important if that's the career path you wish to take. VLSI refers to the design of the chip. It has nothing to do with the manufacturing. Okay. Manufacturing of microchips is a highly specialized skill set. And well, that happens when when you go higher up. You're going to specialize in power systems. You're going to specialize in VLSI design. You might specialize in RF, microwave, antenna. You can specialize in lots of things, right? So as you go higher up. So VLSI fabrication is different from VLSI design. Fabrication is a whole different skill set. It requires expensive manufacturing facilities. It's a very expensive process. It requires clean rooms. So nowadays you hear about like how Apple's designing their own chip, or NVIDIA is making these chips, or AMD is making these chips. Well, nobody is making their chips. They can't make their chips. Okay, it's not something they can do. There's only a few companies in the world that can actually make microchips. There's Intel, there's Samsung Semiconductor, there's Texas Instruments, used to. I don't know if they do any big chips anymore. There are a few companies in Japan. There's Micron, but the big ones are TSMC, and there is MediaTek. They are located in Taiwan. Okay, and TSMC is now the world leader in fabrication technology. You ever seen those videos or pictures with people gowned up in white bunny suits from head to toe inside like white rooms? Anyone ever see a picture or a video like that, right? Those are clean rooms. They are known as clean rooms because the environment is very, very clean. So give you an idea of how clean it is. In normal classroom like this, or normal, outside, you can have 1 million or 2 million particles of size 5 micron or less, or 0.5 microns or less in 1 cubic centimeter. Okay, 1 million or 2 million particles. Inside a clean room, it is less than 1,000. Okay, less than 1,000 in academic clean rooms. So when I went to grad school, I was worked in a clean room that had 2 bays, which were class 100, meaning less than 100 particles, compared to a couple of million outside. Industrial clean rooms, it's less than like 1. Okay, it's that clean. And so that's why it's known as a clean room. If you ever see a medical show, sometimes you have these patients inside behind these, filtered lines, and they say that's a clean room. It is kept clean. Everybody's gowned up so as to prevent contamination from germs and bacteria. All right, coming back to your career pathway. There is a clean room on campus in Cal Poly. Anybody know where that is? That's a good point, actually. There's one in our building, but that's not quite a clean room. I'd actually forgotten about that. Okay, great. So it is, what we have in there is a glove box system that's in room 105. If you've ever been passing by, see there's a polymer electronics course that is listed on there. That's not been offered for a long time because the professor retired. Before he retired, he trained me and Ben Hawkins, who is no longer with EE, to take over the class, but the equipment's not up and running. So we need to get up and running before that. But an actual clean room exists on campus. It's in building 41, engineering 4 or 3 or something. No, not Bonderson. It's attached to the aerospace building. I don't know what it's called. It's where the IME and the materials engineering department is. It's up on the 2nd floor. Yeah. No, this is engineering 4. So the clean room is where we actually build microchips. We use silicon wafers. Students come in every single week. We gown up.